In the quiet darkness above your head, the moon is about to perform an ancient ritual that has terrified civilizations for millennia, transforming from silver guardian into a crimson eye that watches Earth with the intensity of dying stars. Tonight, you'll discover why this celestial alchemy doesn't just change the moon's appearance, but reveals a hidden truth about the delicate cosmic dance that keeps our world alive. What you're about to learn will forever change how you see that familiar face in the night sky, turning every future glance upward into a reminder of the beautiful violence happening in the space between worlds. What transforms the moon from Earth's gentle silver guardian into a glowing ember suspended in the cosmic dark, as if the universe itself were holding a lantern made of starfire and shadow? In the vast theatre of space, where distances stretch beyond imagination and celestial bodies dance to gravitational rhythms older than Earth itself, something magnificent unfolds when our planet steps between the sun and moon. Earth's shadow reaches across the void like a cosmic hand, extending nearly 1.4 million kilometers into the darkness, grasping for its celestial companion with mathematical precision that would humble the greatest architects. When this invisible shadow finally finds the moon, something extraordinary begins, a transformation that has inspired fear, wonder, and worship throughout the entire span of human history. The familiar silver disk that has guided countless generations through dark nights begins to blush with the deep red of sunset, as if the moon itself were embarrassed at some cosmic secret it can no longer hide. This celestial metamorphosis, known as a lunar eclipse, occurs only when Earth positions itself perfectly between the sun and moon, casting our planet's shadow across the lunar surface with geometric exactness. The alignment must be so precise that even slight variations in the moon's elliptical orbit can determine whether Earth's shadow will miss entirely, graze the lunar edge, or engulf it completely in darkness. Yet the moon doesn't simply disappear into the void as logic might suggest. Instead, it glows with an otherworldly crimson light that seems to pulse with mysterious life against the star-scattered darkness. This ethereal illumination emerges from one of nature's most elegant optical phenomena, where Earth's atmosphere transforms from a simple blanket of gases into a cosmic lens of extraordinary sophistication. As sunlight encounters Earth's atmospheric edge during the eclipse, something remarkable happens. The same thin shell of air that protects all life on our planet begins to bend and filter the sun's harsh white light around our world's curved perimeter. Shorter blue wavelengths scatter away into space, just as they do during our daily sunsets, while longer red and orange wavelengths penetrate through the atmospheric layers and curve around Earth's edge through the process of refraction. This atmospheric alchemy acts like a massive ring of fire surrounding our planet, visible only from space, where Earth appears crowned with a thin circle of orange and red light. These warm, filtered rays then travel across the vacuum of space to bathe the moon in their gentle glow, creating the blood moon effect that has captivated human consciousness since our ancestors first looked up at the night sky. The intensity and exact color of this crimson illumination depend on the current state of Earth's atmosphere. Volcanic eruptions can darken the blood moon to deep copper or even make it nearly invisible, while clear atmospheric conditions create brilliantly red eclipses that seem to glow with internal fire. In this way, each blood moon becomes a unique atmospheric fingerprint, revealing the health and composition of Earth's gaseous envelope at that precise moment in time. The transformation unfolds gradually, like a celestial sunrise in reverse. Earth's shadow first touches the moon's eastern edge, creating a subtle darkening that slowly spreads across the familiar lunar landscape. As the shadow deepens, the moon's silvery brightness fades, replaced by the warm crimson glow that seems to emerge from within the lunar surface itself. During the peak moments of totality, when the moon rests completely within Earth's shadow, something profound occurs. The harsh light that normally bleaches out subtle details on the lunar surface disappears, allowing observers to see the moon's ancient features with unusual clarity. Impact craters become more defined, Mountain ranges cast deeper shadows, and the Maria, those dark patches once thought to be lunar seas, reveal their true nature as vast plains of hardened lava from the moon's violent youth. This crimson awakening represents more than just a beautiful celestial spectacle. It demonstrates the intricate gravitational choreography that governs our solar system, where three celestial bodies must align with precision, measured in arc-seconds across distances of millions of kilometers. The blood moon serves as a visible reminder that we live within a cosmic mechanism of extraordinary complexity, where the same forces that created our planet continue to orchestrate these magnificent displays of celestial theatre, each one a testament to the mathematical elegance underlying the apparent chaos of the universe. Why did the sight of the moon bleeding crimson across the night sky send entire civilizations into rituals of desperate protection, as if the very foundations of reality were cracking above their heads? For countless generations spanning thousands of years, the appearance of a blood moon struck terror into human hearts across every continent and culture, creating a universal response that transcended language, geography, and time itself. This wasn't the mild unease of witnessing something unusual, but primal fear that reached into the deepest parts of human consciousness, triggering survival, instincts that recognized cosmic disruption as existential threat. Ancient Mesopotamians, those earliest astronomers who mapped the heavens with mathematical precision, believed a blood moon signaled that demons were devouring the lunar goddess Nana. Their cuneiform tablets describe frantic rituals where priests would beat drums and sound horns throughout the eclipse, creating cacophonous noise intended to frighten away the celestial predators. These weren't primitive people responding to ignorance. They were sophisticated mathematicians who could predict eclipses years in advance, yet still felt compelled to act against cosmic catastrophe. Half a world away, Inca civilizations developed their own interpretation of the Crimson Transformation, believing that a cosmic jaguar was consuming the moon piece by piece. The Inca understood this celestial predator might turn its supernatural hunger toward Earth itself, devouring crops, animals, and ultimately human civilization. Their response involved entire communities gathering to shout and throw spears at the darkened moon, attempting to wound the invisible jaguar and force it to release its lunar prey. These weren't merely superstitions born from ignorance, but rational responses to witnessing something that fundamentally defied the natural order these cultures understood. The moon served as humanity's most reliable companion, a celestial timekeeper that regulated agricultural cycles, navigation, and the very rhythm of human activity. When this constant, dependable presence suddenly transformed into something alien and ominous, the psychological impact resonated through entire civilizations. In medieval Europe, where celestial events were interpreted through the lens of divine will and cosmic judgment, blood moons were seen as omens of plague, war, or the approaching end times. European chroniclers meticulously recorded lunar eclipses alongside accounts of famine, disease, and political upheaval, creating historical documents that linked celestial phenomena to earthly suffering. The blood moon's red color evoked associations with warfare and death, reinforcing cultural narratives about cosmic warnings delivered through astronomical signs. Across the ocean, Native American tribes developed more nuanced interpretations that revealed sophisticated understanding of natural balance. Many tribes saw blood moons as the moon falling ill and needing healing ceremonies to restore cosmic health. The Lakota believed the moon was being attacked by a great bear, while the Hoopa tribe of California interpreted the red coloration as the moon being wounded and bleeding. These cultures responded with healing rituals, songs, and ceremonies designed to nurse their celestial companion back to health. The universality of fear responses to blood moons reveals something profound about human nature that transcends cultural boundaries. Our species evolved under consistent lunar cycles that governed everything from tidal patterns to nocturnal predator behavior. When the moon's familiar appearance suddenly changed, it triggered deep psychological recognition that cosmic stability, the foundation of predictable natural patterns, might be threatened. This instinctive connection between celestial events and earthly affairs wasn't entirely unfounded. Modern statistical analysis has revealed intriguing correlations between astronomical events and historical turning points, though the mechanisms remain mysterious. The blood moon of 1453 coincided with the fall of Constantinople, while lunar eclipses marked significant moments during the American Civil War and both World Wars. Whether these connections represent causation, coincidence, or selective memory remains a subject of scholarly debate. The ancient fear of blood moons also demonstrates humanity's remarkable ability to recognize patterns across vast scales of time and space. Without understanding orbital mechanics or atmospheric physics, our ancestors correctly identified that blood moons represented cosmic events of extraordinary rarity and precision. Their fear responses, while expressed through cultural and religious frameworks, acknowledge the fundamental truth that celestial phenomena operate according to forces beyond human control. Perhaps, most remarkably, these ancient fears preserved crucial astronomical observations through oral traditions and written records that modern scientists now use to study historical eclipse patterns. The terror that blood moons inspired in our ancestors motivated them to document these events with careful attention to timing, appearance, and associated earthly events, creating an unbroken chain of observations that spans millennia. In recognizing the ancient fear of blood moons, we glimpse the profound relationship between human consciousness and cosmic phenomena, a connection that modern urban living has obscured but never eliminated. The same psychological patterns that drove our ancestors to ritual protection still resonate within us, reminding us that we remain fundamentally connected to the cosmic rhythms that govern our celestial home. How does the universe manage to thread a needle across nearly 400,000 kilometers of space with such perfect precision that three celestial bodies, each following their own gravitational destiny, align to create moments of cosmic artistry? The cosmic choreography that creates a blood moon requires a precision that borders on the miraculous, demanding mathematical exactness that would challenge the most sophisticated engineers. Earth, moon, and sun must align with tolerances measured in arc minutes across the vast emptiness of space, creating what astronomers call syzygy, a straight-line configuration of celestial bodies whose name derives from ancient Greek, meaning yoked together, like cosmic oxen pulling the same celestial plough. This extraordinary alignment occurs roughly twice per year, though the intricate dance of orbital mechanics ensures that the moon doesn't always pass through the deepest part of Earth's shadow. The moon's orbit tilts approximately 5.1 degrees relative to Earth's orbital plane around the sun, creating a cosmic geometry where perfect alignment happens only when the moon crosses the ecliptic plane at precisely the right moment. Most months, the moon passes slightly above or below Earth's shadow, missing the chance for eclipse entirely. The shadow itself reveals the elegant physics of light and geometry operating on astronomical scales. Earth casts two distinct shadow regions into space: the umbra, where our planet completely blocks the sun's light, and the penumbra, where only partial blocking occurs. The umbra forms a cone of absolute darkness that extends approximately 1.4 million kilometers beyond Earth, a distance so vast it could contain nearly 4 round trips to the moon. Within this umbral cone, the geometry becomes even more refined. The shadow narrows as it extends away from Earth, following the mathematical laws of perspective and light propagation. At the moon's average distance of 384,400 kilometers from Earth, the umbra measures roughly 9,200 kilometers in diameter, about 2.6 times wider than the moon itself. This seemingly generous margin actually represents precise cosmic engineering, as the moon's elliptical orbit means it sometimes ventures closer to Earth and sometimes farther away, requiring this shadow buffer to ensure reliable eclipse conditions. When the moon travels through the umbra during its monthly journey around Earth, the total lunar eclipse creates the blood moon effect that has captivated humanity for millennia. The moon must spend at least part of its time within this zone of complete shadow for the characteristic red glow to emerge. The duration of totality depends on how deeply the moon penetrates into the umbral cone. Central eclipses, where the moon passes through the shadow center, can last nearly 2 hours, while grazing eclipses may produce totality for only minutes. Penumbral eclipses represent the shadow's subtler artistry, occurring when the moon passes through only the outer shadow region, where Earth partially blocks sunlight. These events produce gentle dimming that many observers never notice without careful attention. The penumbra extends much farther than the umbra, creating a zone of graduated shadow that can affect the moon even when total eclipse doesn't occur. Experienced eclipse watchers can detect penumbral darkening as a slight dulling of the moon's normal brightness, like cosmic twilight settling across the lunar landscape. The mathematical precision required for these alignments demonstrates the clockwork nature of celestial mechanics operating across scales that dwarf human comprehension. Earth orbits the Sun at approximately 30 kilometers per second, while the Moon circles Earth at about 1 kilometer per second. For eclipse alignment to occur, these vastly different orbital speeds must synchronize with the Moon's position relative to the ecliptic plane, creating temporal windows measured in hours during which eclipse becomes possible. Ancient astronomers recognized these patterns thousands of years before understanding the underlying physics, discovering the Saros cycle, an 18-year, 11-day pattern that allows eclipse prediction based purely on observational records. Babylonian astronomers used this cycle to predict eclipses with remarkable accuracy, demonstrating that the cosmic geometry of shadows follows mathematical rules discoverable through patient observation and careful record-keeping. The orbital mechanics governing these alignments also reveal why lunar eclipses are visible from entire hemispheres of Earth simultaneously, unlike solar eclipses that create narrow paths of totality. When the moon enters Earth's shadow, anyone on the night side of our planet can witness the event, sharing the cosmic spectacle across continents and time zones. This global visibility contributed to the universal cultural impact of blood moons throughout human history. Modern space missions have provided unprecedented insights into shadow geometry by observing eclipses from multiple perspectives simultaneously. Satellites positioned at different points in space can map Earth's shadow with extraordinary precision, revealing subtle variations caused by atmospheric refraction and the moon's slightly non-uniform gravitational field. These observations confirm that the cosmic geometry creating blood moons operates with mechanical precision that validates our understanding of gravitational physics and orbital dynamics. The geometry of shadows thus transforms what appears to be a simple alignment into a demonstration of the universe's mathematical elegance, where gravitational forces, orbital velocities, and geometric relationships combine to create predictable celestial performances that unfold with the reliability of cosmic clockwork across the infinite theater of space. Earth's atmosphere becomes a cosmic alchemist during a lunar eclipse, performing feats of optical transformation that would seem like magic if we didn't understand the elegant physics underlying this celestial chemistry. This thin shell of gases transforms into a lens powerful enough to bend starlight around an entire planet, painting the moon with colors that exist nowhere else in the solar system. This atmospheric magic transforms harsh white sunlight, the same brilliant radiation that powers photosynthesis and drives weather systems, into the gentle red glow that bathes the moon in otherworldly luminescence during eclipse totality. The transformation begins when sunlight encounters the thin boundary between space and Earth's gaseous envelope, a zone barely 100 kilometers thick that contains all the air molecules responsible for sustaining life on our planet. Here, in this narrow atmospheric interface, occurs one of nature's most beautiful optical phenomena through a process called Rayleigh scattering, named after the British physicist who first explained why the sky appears blue and sunsets glow red. As individual photons of sunlight penetrate Earth's atmosphere during the eclipse, they collide with gas molecules, primarily nitrogen and oxygen, that are much smaller than the wavelength of visible light. These molecular encounters follow precise physical laws that determine which colors scatter away and which continue their journey toward the moon. Shorter blue wavelengths, with their higher energy and frequency, interact more strongly with atmospheric molecules and scatter in all directions, disappearing into space like cosmic confetti. Meanwhile, longer red and orange wavelengths, carrying less energy per photon, pass through the atmospheric gauntlet with minimal deflection. These survivors encounter Earth's curved atmosphere and experience something remarkable, The same gravitational field that holds our atmosphere in place also bends light rays as they graze our planet's edge. The atmosphere acts like a massive spherical lens 12,800 kilometers in diameter, refracting these red wavelengths around Earth's circumference and focusing them into the shadow cone behind our planet. This atmospheric lens creates a ring of red light surrounding Earth, visible only from space, where our planet appears crowned with a thin circle of orange and crimson fire. Astronauts on the International Space Station have photographed this phenomenon during lunar eclipses, revealing how Earth's atmosphere transforms our world into a cosmic lighthouse that broadcasts red light across hundreds of thousands of kilometers to illuminate the moon. The intensity and exact color of this atmospheric illumination vary dramatically based on the current state of Earth's gaseous envelope, creating a unique atmospheric fingerprint for each blood moon. Volcanic eruptions inject fine ash particles and sulfur dioxide into the stratosphere, where these aerosols persist for months or years, scattering light more efficiently and reducing the amount of red illumination reaching the moon. The massive 1883 Krakatoa eruption created atmospheric disturbances so severe that blood moons appeared unusually dark for nearly 3 years afterward, with some eclipses becoming nearly invisible to the naked eye. Conversely, periods of clear atmospheric conditions, with minimal dust, pollution, or volcanic activity, create blood moons so brilliant they seem to glow with internal fire. These pristine atmospheric states allow maximum red light transmission, producing eclipses where the moon shines with deep copper or bright orange illumination that remains easily visible even in moderately light-polluted skies. The difference between dark and bright blood moons can span several magnitudes of brightness, demonstrating the dramatic impact of atmospheric composition on eclipse appearance. Modern atmospheric science has revealed additional complexities in this optical alchemy. Water vapor in the atmosphere affects how efficiently red light bends around Earth's edge, while ozone concentrations influence the exact wavelengths that successfully navigate the atmospheric obstacle course. Seasonal variations in atmospheric density, caused by temperature changes and weather patterns, create subtle differences in eclipse brightness, even under otherwise similar conditions. Climate scientists now use historical blood moon observations as proxy data for understanding past atmospheric conditions, analyzing ancient eclipse records to study volcanic activity, air quality, and atmospheric compositions spanning centuries before instrumental measurements began. Medieval chroniclers' descriptions of particularly dark or bright lunar eclipses provide valuable information about atmospheric states during historical periods, revealing connections between celestial observations and terrestrial environmental conditions. The atmospheric filtering process also demonstrates the remarkable interconnectedness of Earth's systems, where surface conditions directly influence cosmic phenomena visible from space. Forest fires, dust storms, industrial pollution, and even seasonal changes in vegetation can affect the appearance of blood moons, creating visible links between human activity and astronomical observations. This connection transforms each blood moon into a cosmic mirror that reflects the current health and composition of our planet's atmospheric envelope. Perhaps most remarkably, this atmospheric alchemy operates continuously around Earth's terminator, the boundary between day and night, where sunrise and sunset colors emerge from the same Rayleigh scattering process that creates blood moon illumination. During every eclipse, Earth's entire ring of simultaneous sunrises and sunsets combines to paint the moon with the collective glow of all the beautiful skies on our planet, creating a celestial artwork that represents the atmospheric conditions of an entire world, captured in a single moment of cosmic alignment. The moon's journey through Earth's shadow follows an ancient choreography governed by the fundamental forces that shape our solar system, a gravitational ballet that began billions of years ago when cosmic violence gave birth to celestial harmony. This orbital dance emerged from the chaos of planetary formation when gravitational interactions between Earth and its newly formed satellite gradually settled into the stable patterns that govern lunar motion today. The story begins in the early solar system, approximately 4.5 billion years ago, when a Mars-sized object called Theia collided with the young Earth in a cataclysmic impact that vaporized rock and flung debris into space. From this cosmic catastrophe, gravitational forces gradually gathered the scattered material into what would become our Moon, initially orbiting much closer to Earth than it does today. Over geological time, tidal interactions between the two bodies established the complex orbital relationship that makes modern lunar eclipses possible. The Moon's elliptical orbit creates a dynamic geometry that ensures no two blood moons appear exactly alike. This orbital ellipse, with its varying distance from Earth, means that lunar eclipses occur at different points in the Moon's monthly journey, creating blood moons of dramatically different sizes and durations. The orbital mechanics follow Kepler's laws with mathematical precision, where the Moon's speed varies inversely with its distance from Earth, creating a cosmic rhythm that influences every aspect of eclipse timing. When the Moon reaches perigee, its closest approach to Earth at approximately 356,000 kilometers, it appears roughly 14% larger in our sky than during apogee, its most distant point at about 407,000 kilometers. These perigee eclipses create spectacular supermoon blood moons that seem to dominate the night sky with their imposing presence. The Moon's increased apparent size means it fills more of Earth's shadow, but its faster orbital velocity at perigee causes it to transit the shadow more quickly, shortening the duration of totality. Conversely, eclipses occurring near apogee present the Moon as a smaller, more distant disk that moves through Earth's shadow with leisurely precision. These apogee blood moons can remain in totality for nearly 2 hours, seeming to hang motionless in the cosmic night, like celestial meditation on the nature of time itself. The Moon's slower orbital speed at apogee allows observers to study the gradual color changes and subtle variations in eclipse brightness that unfold across extended periods of totality. The inclination of the Moon's orbit relative to Earth's orbital plane around the Sun, approximately 5.1 degrees, creates the fundamental reason why eclipses don't occur every month, despite the Moon's regular 29.5-day cycle. This orbital tilt means the Moon usually passes slightly above or below Earth's shadow during its monthly journey, missing the precise alignment necessary for eclipse. Only when the Moon crosses the ecliptic plane at the exact moment of full moon phase do the geometric conditions align for lunar eclipse to occur. The gravitational mechanics governing this orbital inclination result from the complex three-body dynamics involving Earth, Moon, and Sun. Solar gravity constantly tugs at the Moon's orbit, causing the orbital plane to slowly rotate in space through a phenomenon called precession. This precession cycle takes 18.6 years to complete, creating the long-term patterns that ancient astronomers discovered and used to predict eclipse cycles without understanding the underlying gravitational physics. These celestial mechanics reveal gravitational relationships that extend far beyond eclipse phenomena, governing the fundamental stability of the Earth-Moon system. The same gravitational forces that create eclipse alignments also drive the tidal forces that slow Earth's rotation and gradually push the Moon into a higher orbit. This tidal evolution proceeds at a rate of approximately 3.8 centimeters per year, barely measurable but relentless over geological time. The Moon's gravitational influence on Earth extends to maintaining our planet's axial stability, preventing the chaotic wobbling that would create extreme climate variations incompatible with complex life. Without the Moon's stabilizing presence, Earth's rotational axis could tilt by tens of degrees over relatively short geological periods, creating climate swings that would make our world uninhabitable for most life forms. Modern laser ranging experiments, which bounce light off reflectors placed on the lunar surface by Apollo astronauts, measure the Moon's gradual recession with millimeter precision. These measurements confirm that the same gravitational interactions creating today's blood moons are slowly but inevitably changing the Earth-Moon system's geometry. In approximately 600 million years, the Moon will have receded far enough that total lunar eclipses will become impossible, marking the end of an astronomical era that has persisted since complex life first emerged on Earth. The orbital mechanics also create subtle variations in eclipse geometry that influence the appearance and duration of blood moons. The Moon's orbit is not perfectly elliptical, but shows small perturbations caused by solar gravity, Earth's slightly non-spherical shape, and gravitational influences from other planets. These perturbations create minute but measurable changes in eclipse timing, and the exact path the moon follows through Earth's shadow. The dance of orbital mechanics thus reveals how blood moons emerge from the ongoing gravitational conversation between Earth, Moon, and Sun, a cosmic dialogue that began with planetary formation and continues to evolve over timescales that span from the duration of individual eclipses to the evolution of the solar system itself. Each blood moon represents a moment in this vast choreography, where the accumulated effects of billions of years of gravitational interaction create the precise conditions necessary for these spectacular displays of celestial artistry. Throughout recorded history, blood moons have served as celestial witnesses to humanity's greatest moments and tragedies, weaving themselves into the fabric of human civilization like cosmic threads connecting earthly events to the vast rhythms of the universe. These crimson transformations have appeared in the skies above empires rising and falling, wars beginning and ending, and scientific revolutions that changed our understanding of reality itself. The blood moon of February 29, 1504, became an instrument of colonial manipulation when Christopher Columbus found himself stranded in Jamaica with increasingly hostile indigenous peoples who refused to provide food and supplies. Columbus, possessing European astronomical tables that predicted the coming lunar eclipse, gathered the local leaders and claimed he would make the moon disappear as punishment for their treatment of his crew. When the eclipse began and the moon started to darken, the terrified inhabitants begged Columbus to restore their celestial companion, agreeing to provide whatever his expedition needed. This calculated deception demonstrates how astronomical knowledge became a tool of power, with blood moons serving as unwitting accomplices to historical exploitation. The American Civil War witnessed multiple blood moons that soldiers on both sides interpreted as cosmic omens related to their cause. The lunar eclipse of August 1862, visible across the battlefields of Virginia, was seen by Union troops as a sign of coming victory, while Confederate soldiers interpreted the same crimson moon as divine approval for their struggle for independence. These competing interpretations reveal how human psychology projects meaning onto celestial events, finding in blood moons whatever significance serves current hopes and fears. The blood moon of July 27, 1917, cast its red glow over a world in revolutionary upheaval, occurring during the Russian Revolution as Bolshevik forces prepared to seize power from the provisional government. Across Europe, where World War I had already shattered traditional certainties, the blood moon seemed to confirm that the old order was dying. Russian peasants and intellectuals alike saw cosmic significance in the crimson sky, interpreting the eclipse as either divine judgment on the Tsarist system or a harbinger of the socialist future they hoped to build. These celestial events have been meticulously recorded by astronomers across cultures, creating an unbroken chain of observations spanning millennia that represents one of humanity's longest-running scientific projects. Chinese astronomers, working within sophisticated bureaucratic systems that valued celestial record-keeping, documented lunar eclipses as early as 1136 BCE. Their observations were driven by the belief that astronomical events reflected the mandate of heaven, making eclipse prediction essential for political legitimacy. These ancient Chinese records now provide modern astronomers with invaluable data for studying long-term changes in Earth's rotation and the Moon's orbital evolution. Babylonian astronomers developed even more systematic approaches to eclipse observation, discovering mathematical patterns that allowed them to predict future events without understanding the underlying physical mechanisms. Their careful records of eclipse timing and appearance enabled later astronomers to discover the 18-year, 11-day Saros cycle that governs eclipse repetition patterns. This ancient mathematical achievement demonstrates how patient observation and record-keeping could reveal cosmic order even without modern physics, showing that the universe's mathematical nature was accessible to any civilization willing to watch the skies with sufficient care and precision. The intersection of astronomical events with religious history adds another layer to the blood moon's role as historical witness. The blood moon that darkened during the crucifixion of Jesus, mentioned in biblical accounts and early Christian writings, has been astronomically calculated and confirmed by modern eclipse prediction software. Computer models indicate that a lunar eclipse did indeed occur on April 3rd, 33 CE, visible from Jerusalem during the hours following Christ's death. This astronomical confirmation doesn't validate religious interpretations, but it demonstrates how ancient writers accurately observed and recorded celestial events that modern science can verify across nearly 2 millennia. Medieval European chroniclers treated blood moons as omens requiring careful documentation, creating detailed accounts that modern historians use to study both astronomical events and contemporary social conditions. The blood moon of October 1493, occurring just 1 year after Columbus's first voyage to the Americas, was recorded across European monasteries as a sign of impending change in God's plan for humanity. These records now provide climate scientists with information about atmospheric conditions during the medieval period, as the brightness and color of historical blood moons reveal past levels of volcanic activity and air quality. Islamic astronomers during the Golden Age of Baghdad made precise observations of lunar eclipses, combining Greek mathematical traditions with original innovations in observational technique. Their eclipse records preserved astronomical knowledge through Europe's Dark Ages and contributed to the scientific renaissance that eventually produced modern astronomy. The blood moon observations of Al-Battani in the 9th century provided data that Copernicus later used to develop his heliocentric model of the solar system. The Industrial Revolution added new dimensions to blood moon observation, as early photographers captured the first images of lunar eclipses in the 1800s. These pioneering eclipse photographs revealed details invisible to naked-eye observers and began the transformation of astronomy from a purely observational science to one enhanced by technological recording devices. The blood moon of January 31st, 1888, produced some of the first high-quality eclipse photographs, showing the moon's gradual transformation through totality with scientific precision that complemented centuries of written descriptions. Modern eclipse observations continue this ancient tradition of historical witness, but now with global coordination and space-based instruments that provide unprecedented detail about lunar eclipse phenomena. The blood moon of July 27, 2018, was simultaneously observed by millions of people across Asia, Africa, and Europe, while spacecraft monitoring systems provided data about atmospheric effects and lunar surface conditions during totality. These historical intersections between cosmic events and human affairs demonstrate how celestial phenomena have always held profound meaning for civilizations seeking to understand their place in the universe. Blood moons serve as temporal anchors in human history, marking moments when earthly concerns connected to cosmic rhythms and revealing the enduring human need to find meaning in the vast celestial dance that surrounds our small world. While human eyes perceive only the blood moon's dramatic red transformation, the complete electromagnetic story unfolds across wavelengths invisible to our senses, revealing a cosmic symphony playing in frequencies that span from radio waves longer than football fields to gamma rays smaller than atomic nuclei. This hidden electromagnetic drama transforms what appears to be a simple visual spectacle into one of the most complex multi-wavelength events observable in our solar system. The infrared portion of the spectrum tells perhaps the most dramatic story during lunar eclipse. As Earth's shadow engulfs the moon, cutting off the warming solar radiation that normally bathes the lunar surface, the moon's temperature plummets with startling rapidity. Thermal infrared cameras reveal this cosmic cooling in real time, showing how the lunar regolith, the powdery surface layer created by billions of years of meteorite bombardment, loses heat at different rates depending on its composition and density. Rock fragments and boulders retain heat longer than fine dust, creating a thermal map of the lunar landscape that becomes visible only during eclipse conditions. These infrared observations have revealed previously unknown details about lunar geology, including buried rock formations and ancient lava flows that remain hidden under normal illumination. The sudden temperature change, dropping over 100 degrees Celsius in just a few hours, creates thermal stresses that cause the lunar surface to crack and shift, producing minute seismic tremors detectable by sensitive instruments. Radio telescopes monitoring the moon during eclipse detect subtle changes in electromagnetic emissions that reveal the lunar interior's electrical properties. The moon's core, partially molten and containing iron-rich materials, generates weak electromagnetic fields that interact with cosmic radiation and solar wind particles. During eclipse, when the solar wind pressure suddenly decreases as Earth's magnetosphere shields the moon, radio observations can detect changes in these deep electromagnetic signatures, providing insights into the moon's internal structure and thermal state. The ultraviolet spectrum reveals another invisible aspect of lunar eclipse, as Earth's shadow affects the moon's tenuous exosphere, a barely there atmosphere consisting of sodium, potassium, argon, and other trace elements knocked loose from the lunar surface by cosmic ray bombardment and micrometeorite impacts. Ultraviolet spectroscopy can detect individual atoms of these elements floating above the lunar surface, monitoring how the eclipse's changing conditions affect this gossamer atmosphere. When solar wind pressure drops during Earth's shadow passage, the lunar exosphere expands and changes composition as fewer atoms are stripped away by charged particles. Some elements, like sodium, create distinct ultraviolet emission lines that allow scientists to map the three-dimensional structure of the lunar atmosphere and study how it responds to changing space weather conditions. These observations have revealed that the moon's exosphere extends much farther into space than previously thought, creating a faint halo of scattered atoms that follows the moon in its orbit around Earth. X-ray observations during lunar eclipse provide unique insights into how cosmic radiation interacts with the shadowed lunar surface. Normally, solar X-rays dominate the lunar electromagnetic environment, but during eclipse, background cosmic radiation becomes the primary source of high-energy photons striking the moon. X-ray telescopes can observe how these cosmic rays penetrate the lunar regolith and interact with different mineral compositions, creating characteristic X-ray fluorescent signatures that reveal the chemical composition of the lunar surface. The absence of solar X-ray bombardment during eclipse also allows sensitive instruments to detect the moon's own faint X-ray emissions, produced by radioactive decay of elements within lunar rocks and by cosmic ray interactions with the surface. These native lunar X-rays provide information about the moon's formation and early history, preserving evidence of the violent processes that created our satellite 4.5 billion years ago. Gamma-ray observations add another layer to this electromagnetic investigation, monitoring how eclipse conditions affect the rate of radioactive decay in lunar materials. While radioactive decay rates are generally considered constant, some theoretical models suggest that gravitational or electromagnetic fields might influence nuclear processes under extreme conditions. Gamma-ray detectors use lunar eclipses as natural laboratories to test these theories, searching for any variations in decay rates that might reveal new physics operating at the intersection of nuclear and gravitational forces. The moon's weak but detectable magnetic field, preserved in rocks from the early solar system when the lunar core was more active, creates subtle variations in how Earth's shadow affects different lunar regions. Spacecraft equipped with magnetometers have mapped these ancient magnetic signatures, revealing that the moon once possessed a global magnetic field similar to Earth's, but lost it as the lunar core cooled and solidified. During eclipse, the changing electromagnetic environment allows more precise measurement of these fossil magnetic fields, providing insights into the moon's thermal and geological evolution. Multi-wavelength studies during lunar eclipse have also revealed unexpected connections between the moon and Earth's upper atmosphere. As the moon passes through Earth's magnetotail, the elongated portion of our planet's magnetic field stretched by solar wind, radio and plasma wave instruments detect complex electromagnetic interactions between lunar magnetic anomalies and Earth's magnetic field lines. These interactions create standing waves and resonances that propagate through the space between Earth and Moon, demonstrating that the two bodies remain electromagnetically connected even across the vacuum of space. Perhaps most remarkably, this comprehensive electromagnetic view reveals that the blood moon represents just the visible manifestation of a complex electromagnetic storm affecting the entire Earth-Moon system. From radio waves that probe the lunar interior to gamma rays that reveal nuclear processes in ancient rocks, the eclipse creates a multi-wavelength laboratory that spans nearly the entire electromagnetic spectrum, transforming our satellite into a cosmic instrument for studying fundamental physics, planetary geology, and the invisible forces that shape our solar system. The blood moon marks a moment when Earth's gravitational relationship with its satellite enters a unique configuration, creating subtle but measurable effects on our planet's tidal systems that demonstrate how cosmic alignments translate into earthly consequences across every ocean, bay, and tidal estuary on our world. This celestial choreography transforms abstract astronomical events into tangible forces that reshape coastlines, influence marine ecosystems, and affect the daily rhythms of life itself. During a lunar eclipse, the Sun, Earth, and Moon align to create what astronomers call syzygy, a cosmic arrangement that intensifies the gravitational forces responsible for generating tides. These enhanced tidal effects, known as spring tides, occur roughly twice each month regardless of eclipse conditions, but the perfect three-body alignment during a blood moon represents the peak of gravitational cooperation between our two nearest celestial neighbors, creating tidal extremes that can exceed normal ranges by significant margins. The physics underlying this tidal response reveals the elegant simplicity of gravitational interactions operating on planetary scales. Earth's oceans respond to the combined gravitational pull of both Moon and Sun, creating two tidal bulges that follow our planet's rotation, one facing toward the Moon and Sun, where gravitational attraction is strongest, and another on the opposite side, where centrifugal forces from Earth's orbital motion create a compensating bulge. During blood-moon alignment, these bulges reach maximum amplitude as lunar and solar gravitational forces combine constructively rather than working at cross purposes. Coastal regions worldwide experience these enhanced tidal conditions as dramatically higher high tides and correspondingly lower low tides that can expose marine habitats, normally underwater or flood areas typically above sea level. The Bay of Fundy, famous for having the world's highest tides, can experience ranges exceeding 16 meters during eclipse-enhanced spring tides, transforming vast areas of seafloor into temporary terrestrial landscapes twice each day. Similar extreme conditions occur in tidal bores, waves that travel up rivers against the current, where eclipse alignment can create surging walls of water that penetrate much farther inland than normal tides. Marine ecosystems have evolved intricate relationships with these cosmic tidal rhythms, creating biological clocks that synchronize reproductive cycles, feeding behaviors, and migration patterns to gravitational influences that originate millions of kilometers away in space. Horseshoe crabs coordinate their spawning to coincide with spring tide conditions, when higher waves carry their eggs farther up beaches and provide optimal conditions for larval development. Coral reefs release gametes during specific tidal phases, creating synchronized spawning events that depend on precise tidal timing to ensure reproductive success. Intertidal creatures demonstrate remarkable adaptations to these gravitational cycles, with Grunion fish in California timing their spawning runs to coincide with the highest spring tides that carry them to optimal beach spawning sites. During blood moon events, these already dramatic spawning runs become even more spectacular, as enhanced tides create perfect conditions for reproductive success. Tidal pool organisms experience extended exposure periods during extreme low tides, triggering adaptive behaviors that help them survive until the returning waters restore their marine environment. Ancient coastal civilizations developed sophisticated understanding of these eclipse-enhanced tidal patterns, incorporating astronomical observations into practical activities that depended on tidal extremes. Pacific Northwest indigenous peoples timed major fishing expeditions to coincide with spring tide conditions, when lower low tides exposed rich intertidal harvesting areas normally submerged. Celtic and Norse coastal cultures planned important ceremonial gatherings around eclipse events, recognizing the spiritual significance of moments when cosmic forces created dramatic changes in familiar tidal landscapes. Medieval European monks, many of whom lived in coastal monasteries, kept detailed records of tidal patterns and their correlation with astronomical events. These records, preserved in monastery archives, provide modern researchers with centuries of tidal data that reveal long-term changes in Earth's rotation rate and tidal evolution. The gradual slowing of Earth's rotation caused by tidal friction becomes measurable only through these historical records spanning multiple centuries. Modern tidal prediction systems incorporate these astronomical influences through complex mathematical models that account for the gravitational effects of Moon, Sun, and even major planets on Earth's oceanic systems. Harmonic analysis techniques break down tidal patterns into constituent components, each corresponding to specific astronomical cycles ranging from daily rotation to the 18th six-year lunar nodal cycle. Blood moon events represent convergence points where multiple harmonic components align to create maximum tidal amplitudes. Coastal engineering projects must account for these extreme tidal conditions when designing seawalls, harbours, and flood protection systems. The highest tides often occur during eclipse-enhanced spring tide conditions, requiring infrastructure that can withstand gravitational forces amplified by precise cosmic alignment. Storm surge models incorporate these tidal enhancements, recognizing that hurricanes or coastal storms arriving during blood moon periods can create flooding conditions far beyond normal storm surge predictions. The global nature of tidal response during blood moon events demonstrates the interconnectedness of Earth's oceanic systems, where gravitational influences create synchronized tidal patterns across ocean basins spanning thousands of kilometers. Tidal waves generated by eclipse-enhanced gravitational forces propagate across ocean basins at speeds determined by water depth, creating complex interference patterns where Atlantic and Pacific tidal systems interact through narrow straits and channels. Modern satellite altimetry provides unprecedented ability to monitor these global tidal responses during eclipse events, revealing subtle variations in ocean surface height that occur as gravitational forces shift during the eclipse progression. These measurements confirm theoretical predictions about tidal mechanics while revealing previously unknown complexities in how ocean basins respond to changing gravitational configurations. Perhaps most remarkably, these tidal responses during blood moon events demonstrate how cosmic mechanics continue to shape terrestrial processes in measurable ways, connecting the rotation of planets and the orbital dance of celestial bodies to the daily rhythms of life in tidal zones around the world. Every blood moon creates a global experiment in gravitational physics, where abstract celestial alignments translate into tangible forces that move vast quantities of water and influence the behavior of countless marine organisms across our blue planet. As Earth's shadow envelops the moon during a blood moon, the lunar surface transforms into a natural laboratory where secrets normally hidden beneath the glare of direct sunlight emerge into view, revealing the moon's geological biography written in dust, rock, and the scars of cosmic violence spanning billions of years. This sudden transition from blazing illumination to gentle red twilight creates conditions that exist nowhere else in the solar system, allowing scientists to study lunar geology through a completely different electromagnetic lens. The dramatic cooling caused by the eclipse creates immediate thermal stresses throughout the moon's regolith. The layer of pulverized rock and fine dust that blankets the lunar surface like cosmic snow accumulated over geological ages. This regolith, created by billions of years of meteorite bombardment that shattered solid bedrock into particles ranging from boulder-sized fragments to powder finer than flour, responds to rapid temperature changes in ways that reveal its complex internal structure and composition. During normal daylight conditions, the lunar surface reaches temperatures exceeding 120 degrees Celsius, hot enough to boil water. But within hours of eclipse totality, these same areas plummet to minus 170 degrees Celsius, creating thermal gradients so severe they generate mechanical stresses throughout the regolith layer. Different materials contract at different rates as they cool, causing the lunar surface to crack and shift in patterns that produce faint seismic tremors detectable by sensitive instruments both on the lunar surface and in orbit around the moon. These thermal moonquakes, first detected during Apollo missions and confirmed by modern lunar monitoring equipment, reveal how the regolith behaves as a complex granular material rather than solid rock. The shifting and settling creates acoustic signals that propagate through the lunar interior, providing seismologists with data about subsurface structure and the depth of the regolith layer in different regions. Some areas show regolith depths of only a few meters, while others contain dust deposits dozens of meters thick, accumulated in low-lying areas over billions of years. The blood moon's dim red illumination creates unprecedented observing conditions that allow astronomers to study subtle details of the lunar landscape, normally bleached out by harsh solar radiation. Without the overwhelming brightness of direct sunlight, telescopes can detect delicate color variations across the lunar surface that indicate different mineral compositions and geological histories. These spectral signatures, invisible under normal illumination, reveal the chemical fingerprints of ancient volcanic activity, impact events, and space weathering processes. Highlands regions, composed primarily of anorthosite rock, formed during the moon's early magma ocean phase, show distinct reflectance properties under eclipse illumination that reveal their calcium-rich feldspar composition. These ancient crustal rocks, some of the oldest materials in the solar system, preserve evidence of the moon's formation and early bombardment history in their mineral structure and impact crater density. Impact craters become dramatically more defined under the red light of eclipse, as the low-angle illumination creates sharp shadows that reveal subtle topographical details normally invisible. The moon's violent history, written in circular scars from billions of years of cosmic bombardment, emerges with startling clarity as crater walls, central peaks, and ejecta blankets cast distinct shadows across the regolith surface. Some craters show multiple overlapping impact events, creating complex geological relationships that tell stories of sequential cosmic collisions spanning eons. The Maria, those dark patches that early astronomers mistook for lunar seas, reveal their true nature as ancient lava flows under eclipse conditions. These vast basaltic plains, formed when massive impacts fractured the lunar crust and allowed molten rock to erupt from the interior, show subtle color variations that indicate different episodes of volcanic activity. Mare Tranquillitatis, where Apollo 11 first landed, displays distinct spectral signatures that reveal the titanium-rich composition of its ancient lavas, while Mare Imbrium shows evidence of multiple lava flow layers deposited over millions of years. Scientific instruments on lunar orbiters take advantage of eclipse conditions to calibrate their sensors and conduct specialized observations impossible under normal illumination. Thermal infrared cameras can measure the moon's heat retention properties without interference from reflected sunlight, revealing how different materials store and release thermal energy. These measurements provide insights into regolith density, composition, and the presence of subsurface rock formations that influence heat conduction patterns. The moon's tenuous exosphere, a barely there atmosphere consisting of atoms knocked loose from the surface by cosmic ray bombardment and micrometeorite impacts, responds dramatically to eclipse conditions as solar wind pressure suddenly decreases during Earth's shadow passage. Normally, this thin atmosphere of sodium, potassium, argon, and other trace elements remains compressed close to the surface by constant solar wind bombardment. During eclipse, the reduced pressure allows the exosphere to expand, creating measurable changes in atmospheric density and composition. Spectrometers monitoring the lunar exosphere during eclipse detect increased concentrations of surface-derived atoms as the reduced solar wind pressure allows more material to escape into space. These observations reveal the ongoing process of lunar atmospheric evolution, where the moon slowly loses surface material to space through a combination of solar wind sputtering and impact vaporization. The rate of atmospheric loss provides insights into how the moon's surface composition has changed over geological time. Advanced radar systems use eclipse conditions to penetrate deeper into the regolith than normally possible, as the reduced electromagnetic interference from solar radiation allows more sensitive subsurface mapping. These radar investigations have revealed buried crater structures, ancient lava tube networks, and variations in regolith density that indicate different geological processes operating in various lunar regions. Perhaps most remarkably, the eclipse environment allows scientists to study how space weathering processes affect lunar materials over time. The constant bombardment of cosmic rays, solar wind particles, and micrometeorites gradually darkens and alters the chemical properties of regolith grains, creating optical effects that change how the lunar surface reflects light. Under eclipse conditions, these space-weathering signatures become more apparent, revealing how the Moon's appearance has evolved over billions of years of exposure to the harsh space environment. The lunar regolith revealed during blood moon events thus serves as both an archive of solar system history and a laboratory for studying planetary processes under extreme conditions. Each eclipse provides a unique opportunity to examine our nearest celestial neighbour through the gentle filter of Earth's atmosphere, revealing geological secrets that remain hidden under the harsh glare of unfiltered sunlight, and demonstrating how astronomical events can create natural laboratories for planetary science across the vast distances of space. The blood moon occurs within a complex gravitational symphony where Earth, Moon, and Sun create resonances that ripple through the very fabric of space-time itself, transforming what appears to be a simple eclipse into a cosmic experiment in fundamental physics that tests the deepest principles governing reality. These gravitational interactions, while far too subtle for human perception, orchestrate influences that extend from the smallest scales of quantum mechanics to the largest structures of the universe. The gravitational field configuration during lunar eclipse creates a unique three-body system where the combined mass of Earth, Moon, and Sun generates space-time curvature patterns that exist nowhere else in our solar system. Einstein's general relativity describes gravity not as a force but as the curvature of space-time caused by mass and energy, and the precise alignment during blood moon events creates geometric relationships in this curved space-time that allow physicists to test relativistic predictions with extraordinary precision. These gravitational interactions influence everything from the orbits of artificial satellites to the precise measurement of time on GPS systems, which must account for both special and general relativistic effects to maintain accuracy. During eclipse alignment, the combined gravitational field of the three-body system creates subtle perturbations in satellite orbits that require constant monitoring and correction. The GPS constellation, designed to provide location accuracy within meters, must compensate for gravitational time dilation effects that become slightly modified during the unique mass configuration of lunar eclipse. The perfect alignment of Earth, Moon, and Sun during blood moon events theoretically creates conditions where gravitational waves, ripples in the fabric of spacetime predicted by Einstein and first detected in 2015, might experience subtle modifications as the mass distribution in the Earth-Moon-Sun system briefly changes configuration. While these effects remain far below the detection threshold of current technology, advanced gravitational wave detectors like LIGO and Virgo monitor eclipse periods for any measurable perturbations in the background gravitational radiation that constantly permeates the universe. Theoretical calculations suggest that the massive acceleration of the Moon through Earth's shadow might generate gravitational wave signatures with characteristic frequencies related to the eclipse duration and orbital mechanics. These predictions remain at the edge of detectability, but future generations of gravitational wave observatories may achieve sufficient sensitivity to observe these subtle space-time disturbances created by familiar celestial events in our own cosmic neighborhood. The Moon's passage through Earth's shadow also creates a temporary gravitational lensing effect, where our planet's gravity bends light from distant stars, according to Einstein's prediction that massive objects curve space-time and deflect electromagnetic radiation. During eclipse, Earth acts as a gravitational lens that theoretically focuses starlight from sources directly behind our planet, though this effect remains far too small to observe with current astronomical technology. The gravitational lensing calculations for Earth's mass predict light deflection angles measured in micro-arc seconds, thousandths of the angular resolution achievable by the most advanced telescopes. Future space-based observatories operating at the theoretical limits of optical precision might eventually detect these minuscule deflections, providing direct measurements of how Earth's gravitational field affects electromagnetic radiation during eclipse conditions. Particle physicists study blood moon events as natural laboratories for understanding how gravitational fields might influence fundamental particles and quantum mechanical processes. Some theoretical models suggest that gravitational effects could influence the rate of radioactive decay, the behavior of elementary particles, or the propagation of electromagnetic radiation in ways that become measurable only under the extreme precision conditions available during carefully monitored eclipse events. These investigations explore the intersection between gravity and quantum mechanics, two pillars of modern physics that remain fundamentally incompatible in current theoretical frameworks. Blood moon observations provide opportunities to search for subtle quantum gravitational effects that might reveal new physics operating at the boundary between classical general relativity and quantum field theory. Theoretical physicists use eclipse calculations to test the precision of general relativity in complex three-body gravitational systems where multiple massive objects create overlapping curvature patterns in space-time. The Earth-Moon-Sun system during eclipse represents one of the most precisely calculable examples of relativistic mechanics available for experimental verification, allowing researchers to compare theoretical predictions with observational data across timescales ranging from minutes to decades. These calculations must account for subtle effects including the finite speed of gravitational interactions, the influence of Earth's rotation on local space-time geometry, and the complex orbital dynamics that govern the evolution of the eclipse system over time. Any discrepancies between theoretical predictions and observational reality could indicate new physics beyond general relativity or reveal computational effects in multi-body gravitational systems. Advanced timing experiments during eclipse events test whether gravitational field variations affect the fundamental constants of nature or the flow of time itself at levels approaching the theoretical limits of measurement precision. Atomic clocks deployed in different gravitational environments during eclipse provide data about gravitational time dilation effects and the stability of physical constants under varying space-time curvature conditions. The resonance effects extend beyond immediate gravitational influences to encompass the long-term evolution of the Earth-Moon system itself. Tidal forces that create the eclipse alignment also drive the gradual recession of the Moon from Earth, demonstrating how gravitational interactions operate across timescales, from eclipse duration to the age of the solar system. These evolutionary calculations connect blood moon observations to the fundamental dynamics governing planetary system formation and stability. Perhaps most remarkably, modern theoretical physics suggests that gravitational resonances during eclipse events might connect to the quantum vacuum structure underlying empty space itself. Some models propose that gravitational field fluctuations could influence the zero-point energy of the quantum vacuum, creating measurable effects in precision experiments conducted during carefully chosen astronomical alignments. These investigations transform familiar blood moon events into windows for exploring the deepest mysteries of physics and cosmology. The gravitational resonances that create eclipse conditions also provide natural laboratories for testing our understanding of space-time, quantum mechanics, and the fundamental forces that govern reality, from the smallest scales of elementary particles to the largest structures of the observable universe, revealing how even local astronomical events connect to the most profound questions about the nature of existence itself. The blood moon has witnessed the entire evolution of human image-making, serving as both subject and silent observer through humanity's journey from ancient cave paintings depicting celestial events to the sophisticated digital sensors and space-based observatories that now capture eclipse phenomena with precision that would astound our ancestors. This progression of visual technology has transformed our understanding of lunar eclipses from mystical events requiring interpretation through cultural and religious frameworks into precisely documented scientific phenomena that reveal the workings of atmospheric physics and celestial mechanics. The earliest attempts to capture lunar eclipse imagery emerged in the mid-1800s, when pioneering photographers like John Adams Whipple and Warren de la Rue first pointed their primitive cameras at the darkened moon. These early photographic plates required exposures lasting several minutes during totality, as the blood moon's dim illumination challenged the limited sensitivity of silver halide emulsions. During these extended exposures, the moon's continued motion through Earth's shadow created haunting, blurred images that seemed to capture the mystery and ethereal quality of the eclipse, rather than documenting its precise mechanism. These ghostly early photographs revealed unexpected details invisible to naked-eye observers, including the gradual progression of Earth's shadow edge across familiar lunar landmarks, and subtle variations in the eclipse's red illumination that corresponded to different atmospheric conditions. The photographic plates recorded information that human vision missed, demonstrating for the first time how technological enhancement could extend scientific observation beyond the limitations of biological senses. The technical challenges of eclipse photography drove innovations in camera design and photographic chemistry throughout the late 1800s and early 1900s. Astronomers developed specialized telescope mounts that could track the moon's motion during eclipse, allowing shorter exposures that captured sharper details of the shadow's progression. Improvements in photographic emulsion sensitivity reduced required exposure times and enabled photographers to document the eclipse's changing brightness levels throughout the event. The development of color photography in the early 20th century revolutionized blood moon documentation, transforming eclipse observation from monochromatic light and shadow studies into detailed spectral analysis that revealed atmospheric conditions on Earth during the eclipse. Color films could record the precise hues of eclipse illumination, from deep copper red during eclipses occurring through volcanic ash-laden atmospheres to brilliant orange when clear skies allowed maximum light transmission. These color records became valuable scientific data for understanding how atmospheric composition affects eclipse appearance. Photographic analysis revealed that blood moon colors span a remarkable range depending on atmospheric conditions. Eclipses following major volcanic eruptions, such as the 1991 Mount Pinatubo event, produced photographs showing the moon appearing deep brown or nearly invisible, while eclipses during clear atmospheric periods created images of brilliant copper and orange illumination. This photographic evidence demonstrated the direct connection between Earth's atmospheric health and the appearance of celestial phenomena. Modern digital sensors have revolutionized eclipse photography by capturing the full dynamic range of blood moon illumination, from the deepest shadows of totality to the subtle earthshine that sometimes illuminates the moon's uneclipsed limb. Digital cameras can record brightness variations spanning many orders of magnitude, revealing details that film photography could never capture. High-resolution digital images show individual lunar mountains casting shadows during eclipse, while sensitive sensors detect the faint blue-gray glow of earthshine reflecting from the portion of the moon outside Earth's shadow. The transition to digital photography also enabled real-time image processing and enhancement techniques that extract maximum scientific information from eclipse observations. Computer algorithms can combine multiple exposures taken at different brightness levels, creating composite images that show both the faint red glow of totality and the bright lunar surface features simultaneously. These high dynamic range techniques reveal structural details in the eclipse shadow and atmospheric effects that remain invisible to single exposure photography. Spacecraft photography has provided the most revolutionary advancement in eclipse documentation, offering unprecedented perspectives impossible from Earth's surface. The Lunar Reconnaissance Orbiter and other spacecraft have photographed Earth during lunar eclipses, showing how our planet appears from the moon's perspective, surrounded by a thin ring of red light created by atmospheric refraction. These space-based images reveal the three-dimensional nature of Earth's shadow and demonstrate how the eclipse appears to observers on the lunar surface. Perhaps most remarkably, spacecraft positioned between Earth and Moon have captured images showing both the eclipsed Moon and the Earth's shadow simultaneously, providing a complete view of the eclipse geometry that no terrestrial observer could achieve. These images show Earth's shadow as a dark cone extending into space, with the Moon passing through this zone of darkness, while bathed in the red light refracted through Earth's atmosphere. Time-lapse photography and high-speed video have transformed the blood moon from a static phenomenon into a dynamic celestial performance that reveals the smooth progression of shadow movement across the lunar surface. Modern digital cameras can capture eclipse sequences with temporal resolution measured in seconds, creating movies that compress hours of eclipse progression into minutes of viewing time. These time-lapse sequences reveal subtleties in shadow movement and color changes that individual photographs cannot convey. High-definition video of lunar eclipses captures the gradual darkening and reddening of the moon with cinematic quality that makes the astronomical mechanics visible in real time. The smooth progression of Earth's shadow across lunar craters and mountains becomes apparent in these video sequences, transforming abstract astronomical concepts into visually comprehensible phenomena that demonstrate the reality of our planet's motion through space. Advanced amateur astronomers now routinely capture eclipse photographs that exceed the quality of professional astronomical images from just decades ago. Digital cameras with sophisticated cooling systems and computer-controlled tracking mounts allow dedicated eclipse photographers to document blood moons with scientific precision, creating detailed records that contribute to professional astronomical databases. The democratization of high-quality eclipse photography through digital technology has created a global network of citizen scientists who document blood moon events from locations worldwide, providing comprehensive coverage that no single observatory could achieve. Social media platforms during eclipse events showcase thousands of images captured simultaneously from different geographic locations, creating collective documentation that reveals how atmospheric conditions vary across Earth's surface during the same eclipse. This photographic evolution has transformed blood moon observation from rare, mystical events documented only through written descriptions and artistic interpretations into precisely recorded phenomena that provide quantitative data about atmospheric physics, lunar surface properties, and the mechanics of celestial alignments, demonstrating how technological advancement continuously expands the boundaries of human perception and scientific understanding. Across the vast tapestry of human cultures, the blood moon has inspired mythologies that reveal universal patterns in how our species interprets cosmic phenomena, creating stories that bridge the gap between earthly experience and celestial mystery through narratives that transcend geographical boundaries and historical epochs. These mythological frameworks demonstrate humanity's profound need to find meaning in astronomical events that challenge our understanding of natural order and cosmic stability. Norse mythology wove lunar eclipses into the fabric of cosmic destiny through the legend of Hati, one of two monstrous wolves eternally pursuing the sun and moon across the sky. According to these ancient Scandinavian tales, Hati's successful capture and devouring of the moon during eclipse represented a crucial step in the cosmic struggle leading to Ragnarok, the twilight of the gods and the end of the current world order. The blood moon's red color intensified this apocalyptic symbolism, suggesting that the wolf's attack had wounded the moon and caused it to bleed celestial ichor across the night sky. Viking communities responded to blood moons with elaborate rituals designed to aid the moon in its struggle against the cosmic wolf, creating cacophonous noise with drums, horns, and weapons to frighten away the supernatural predator. These ceremonies reveal how mythological interpretations translated into collective action, demonstrating the practical social functions of cosmic mythology in creating community solidarity during moments of celestial crisis. Hindu astronomical traditions developed sophisticated mythological frameworks around the demon Rahu, whose decapitated head eternally pursues both sun and moon to swallow them in cosmic vengeance. According to these ancient stories, Rahu had attempted to drink the nectar of immortality alongside the gods, but Vishnu discovered the deception and severed the demon's head with his discus. The immortal head, driven by eternal hunger and rage, continues to chase the celestial bodies that betrayed its secret, occasionally catching and swallowing them during eclipse events. This mythological system explained both lunar and solar eclipses through a single narrative framework that connected cosmic events to themes of deception, divine justice, and the consequences of overreaching ambition. Hindu eclipse rituals involved fasting, prayer, and purification ceremonies. The ability to predict blood moons represents one of humanity's greatest intellectual achievements, transforming what once appeared as random cosmic events into precisely calculable phenomena that demonstrate the universe's underlying mathematical nature. This predictive capability spans millennia of human development, from ancient astronomers working with nothing but careful observation and primitive arithmetic to modern astrophysicists employing supercomputers that can model celestial mechanics across geological timescales. The mathematical journey began over 2,500 years ago when Babylonian astronomers, working in the sophisticated urban centers of ancient Mesopotamia, discovered patterns in eclipse timing that seemed to repeat with mysterious regularity. Through centuries of meticulous record-keeping that treated astronomical observation as both scientific endeavor and religious duty, these ancient scholars identified what we now call the Saros cycle, an 18-year, 11-day pattern that allows precise eclipse prediction based purely on observational records without any understanding of the underlying celestial mechanics. This remarkable mathematical relationship emerges from the complex interplay between three fundamental astronomical periods: the Moon's synodic period of approximately 29.53 days, its draconic period of about 27.21 days, and its anomalistic period of roughly 27.55 days. The Saros cycle represents the least common multiple of these three periods, creating a temporal framework where eclipse conditions repeat with extraordinary precision after exactly 223 synodic months, 242 draconic months, and 239 anomalistic months. The mathematical elegance of the Saros cycle reveals how seemingly random celestial motions actually follow deterministic patterns that become apparent only through patient observation across decades of time. Babylonian astronomers recognized that eclipses occurring 18 years and 11 days apart would share similar characteristics, appearing at nearly the same lunar phase, at similar points in the Moon's elliptical orbit, and with comparable durations and geographical visibility patterns. The discovery of this mathematical relationship allowed ancient civilizations to predict eclipses with remarkable accuracy, transforming blood moons from terrifying supernatural events into calculable phenomena that could be anticipated and prepared for. This predictive capability provided enormous political and religious power to the astronomical priesthood, demonstrating how mathematical knowledge could translate into social influence and cultural authority. Modern eclipse prediction has evolved far beyond the Saros cycle into sophisticated computational endeavors that employ differential equations, accounting for gravitational perturbations from every significant body in the solar system. These calculations must consider not only the primary gravitational interactions between Earth, Moon, and Sun, but also the subtle influences of planets, asteroids, and even the Moon's slightly non-uniform mass distribution caused by its complex internal structure and the mascons, mass concentrations beneath the lunar surface. Contemporary eclipse prediction algorithms solve Newton's equations of motion in the three-body problem through numerical integration techniques that track the positions and velocities of celestial bodies with extraordinary precision. These calculations account for relativistic effects predicted by Einstein's general theory of relativity, including the precession of orbital ellipses and the slight delay in gravitational interactions that propagate at the speed of light rather than instantaneously. The computational complexity of modern eclipse prediction requires supercomputers that can process millions of calculations per second, modeling gravitational interactions across timescales spanning from milliseconds to millennia. These computer models can predict blood moons thousands of years into the future, or reconstruct eclipse patterns from the distant past with precision measured in seconds, revealing how eclipse patterns evolve as the Earth-Moon system gradually changes configuration over geological time. Perhaps most remarkably, these long-term calculations reveal that the Moon's gradual recession from Earth, caused by tidal friction that slows Earth's rotation and pushes the Moon into a higher orbit, will eventually end the era of total lunar eclipses. In approximately 600 million years, the Moon will have receded far enough that it will no longer completely fit within Earth's umbral shadow, marking the end of blood moon phenomena and transforming future lunar eclipses into purely penumbral events. The mathematics of eclipse prediction also demonstrates how the slightest changes in initial conditions can cascade through the entire Earth-Moon-Sun system over extended timescales. This sensitivity to initial conditions, a hallmark of chaotic dynamical systems, means that eclipse predictions become increasingly uncertain when extended millions of years into the future, as small uncertainties in current measurements amplify exponentially over time. Modern precision in eclipse prediction depends on extraordinarily accurate measurements of current orbital parameters obtained through laser ranging experiments that bounce light off retroreflectors placed on the lunar surface by Apollo astronauts. These measurements determine the Moon's distance with millimeter precision, providing the baseline data necessary for long-term orbit calculations that account for the Moon's gradual recession and the complex perturbations affecting lunar motion. The computational models used for eclipse prediction have become sophisticated enough to account for previously neglected effects, such as the influence of Earth's changing rotation rate, variations in the planet's magnetic field, and even the gravitational effects of tectonic plate motion that slowly redistributes mass within Earth's interior. These refinements demonstrate how eclipse prediction has evolved into a comprehensive test of our understanding of gravitational physics and planetary dynamics. Artificial intelligence and machine learning algorithms now assist in eclipse prediction by analyzing vast databases of historical observations to identify subtle patterns and correlations that might improve long-term forecasting accuracy. These computational approaches can process observational data spanning centuries to refine models of orbital evolution and gravitational perturbations with unprecedented precision. The mathematical frameworks developed for eclipse prediction have found applications far beyond astronomy, contributing to satellite navigation systems, space mission planning, and the study of exoplanet systems around distant stars. The same computational techniques used to predict blood moons help engineers calculate spacecraft trajectories and assist astronomers in searching for planetary transit events around other suns. Perhaps most profoundly, the mathematics of eclipse prediction reveals the universe's fundamental mathematical nature, where complex astronomical phenomena emerge from simple physical laws operating according to precise mathematical relationships. The ability to predict blood moons demonstrates that the cosmos operates as a vast computational system, where current conditions determine future states according to deterministic rules discoverable through human reason and mathematical analysis. These predictive capabilities connect contemporary eclipse observers to an unbroken chain of mathematical discovery stretching back to ancient Babylon, where the first astronomers realized that the apparent chaos of celestial motions concealed underlying patterns accessible to patient observation and mathematical analysis. Each blood moon predicted and observed validates this ancient insight that the universe operates according to comprehensible mathematical principles that reward careful study with the power to anticipate cosmic events across vast expanses of space and time. Each blood moon carries within its red light a unique atmospheric fingerprint that reveals the current state of Earth's gaseous envelope, transforming lunar eclipses into cosmic diagnostic tools that encode information about air quality, climate conditions, and atmospheric composition in the very photons that paint the moon crimson. This celestial record-keeping system operates on scales both intimate and global, where local weather patterns and worldwide atmospheric circulation combine to create eclipse illumination as unique as human fingerprints. The intensity and precise color of lunar eclipse illumination depend on the complex three-dimensional structure of Earth's atmosphere at the time of the event, including the amount of dust, water vapor, industrial pollution, and volcanic particles suspended throughout the atmospheric column. Each component affects light transmission differently, creating spectral signatures that atmospheric scientists can decode to understand current environmental conditions and long-term climate trends. Water vapor in the atmosphere absorbs specific wavelengths of red light, creating subtle darkening effects that vary with humidity levels and seasonal moisture patterns. Desert regions with extremely dry air allow maximum light transmission, producing brilliant red eclipses, while humid tropical atmospheres create slightly dimmer illumination as water molecules selectively absorb portions of the red spectrum. These moisture effects create regional variations in eclipse brightness that reveal global patterns of atmospheric circulation and seasonal weather systems. Major volcanic eruptions inject massive quantities of fine ash particles and sulfur dioxide into the stratosphere, where these aerosols can persist for months or years, fundamentally altering eclipse appearance across multiple events. The sulfur dioxide converts to sulfuric acid droplets that scatter light with extraordinary efficiency, dramatically reducing the amount of red illumination that successfully navigates Earth's atmospheric gauntlet to reach the moon. The 1991 Mount Pinatubo eruption in the Philippines created some of the darkest blood moons in recorded history, with eclipses appearing deep brown or nearly invisible to naked eye observers for over 2 years following the eruption. Atmospheric scientists used eclipse brightness measurements during this period to study how volcanic aerosols disperse through global circulation patterns and gradually settle out of the stratosphere, providing valuable data about atmospheric residence times and particle removal mechanisms. Conversely, periods of low volcanic activity combined with minimal industrial pollution can produce blood moons of extraordinary brilliance that seem to glow with internal fire. The clear atmospheric conditions during the late 19th century, before widespread industrialization, created eclipse records describing lunar illumination so bright that observers could easily read by the red moonlight during totality. Modern air pollution adds another layer of complexity to atmospheric fingerprinting, as industrial emissions, vehicle exhaust, and particulate matter from urban areas create regional variations in eclipse brightness that correlate with air quality measurements. Eclipses observed from heavily polluted regions appear noticeably dimmer than those viewed from pristine environments, demonstrating how human activity affects even cosmic phenomena through its impact on atmospheric transparency. Climate scientists have discovered that historical eclipse records provide valuable proxy data for understanding past atmospheric conditions, using written descriptions of eclipse color and brightness to reconstruct air quality and volcanic activity patterns stretching back centuries before instrumental measurements began. Medieval chronicles describing unusually dark or bright lunar eclipses now contribute to climate models that attempt to understand natural variability in Earth's atmospheric system. The detailed color descriptions in these historical records reveal information about atmospheric composition during different climatic periods. Eclipse accounts from the medieval warm period describe generally bright red illumination, suggesting clear atmospheric conditions, while records from the Little Ice Age often mention darker, more somber eclipse coloration that may reflect increased volcanic activity or changes in atmospheric circulation patterns. Spectroscopic analysis of eclipsed moonlight has revolutionized atmospheric fingerprinting by allowing scientists to identify specific chemical compounds in Earth's atmosphere through their absorption signatures in the red light that illuminates the moon. Advanced spectrometers can detect trace gases, including ozone, methane, carbon dioxide, and various industrial pollutants by analyzing the precise wavelengths missing from eclipse illumination. These spectroscopic measurements have revealed seasonal variations in atmospheric composition, including changes in ozone concentrations that follow annual cycles of ultraviolet radiation and chemical reactions in the stratosphere. Eclipse spectra obtained during different seasons show how atmospheric chemistry evolves throughout the year, providing insights into the complex photochemical processes that maintain Earth's protective ozone layer. The detection of industrial pollutants in eclipse spectra demonstrates how human activities have fundamentally altered Earth's atmospheric composition since the beginning of industrialization. Compounds like chlorofluorocarbons, nitrogen oxides, and various organic pollutants leave characteristic spectral signatures in eclipse light that allow scientists to track the global dispersion of anthropogenic emissions and study their atmospheric residence times. Forest fire smoke creates distinctive atmospheric fingerprints in blood moon illumination, as the organic particles and gases released by combustion have different light scattering properties than volcanic ash or industrial emissions. Eclipse observations during major wildfire events reveal how smoke plumes spread through regional and continental atmospheric systems, providing data about fire impact on air quality and climate. Seasonal dust storms, particularly those originating in desert regions like the Sahara, create measurable effects on eclipse brightness that allow scientists to study global dust transport patterns. Saharan dust that travels across the Atlantic Ocean to affect air quality in the Americas leaves detectable signatures in eclipse observations made from different geographical locations, revealing the intercontinental scale of atmospheric processes. The blood moon's role as an atmospheric laboratory extends to studying how Earth's gaseous envelope responds to space weather events, including solar storms and cosmic ray bombardment. Changes in upper atmospheric chemistry caused by solar particle bombardment can alter eclipse illumination in subtle ways that provide insights into the coupling between solar activity and terrestrial atmospheric processes. Modern satellite-based atmospheric monitoring systems now complement eclipse observations by providing detailed real-time data about aerosol concentrations, gas compositions, and circulation patterns during eclipse events. This combination of ground-based eclipse observation and space-based atmospheric measurement creates comprehensive datasets that advance our understanding of how Earth's atmosphere affects cosmic phenomena. Perhaps most remarkably, the atmospheric fingerprinting capability of blood moons demonstrates how local environmental conditions on Earth become visible across interplanetary distances, encoded in the red light that travels nearly 400,000 kilometers from our planet's atmospheric edge to the lunar surface. Each eclipse thus represents a moment when Earth's entire gaseous envelope participates in creating a cosmic light show that simultaneously entertains observers and provides scientific insights into the complex atmospheric processes that sustain life on our planet. This transformation of blood moons into atmospheric diagnostic tools reveals the intimate connections between cosmic phenomena and terrestrial environmental conditions, where the same atmospheric processes that affect daily weather and long-term climate also determine the appearance of celestial events visible from anywhere on Earth's night side. Life on Earth has evolved under the rhythmic influence of lunar cycles for over 3 billion years, creating biological clocks so deeply embedded in living systems that the blood moon represents a dramatic disruption to patterns that have remained constant since complex life first emerged from the primordial oceans. These cosmic rhythms have become woven into the very fabric of biology, governing everything from cellular processes to ecosystem-wide behaviors that depend on the moon's predictable presence and appearance. The evolutionary relationship between lunar cycles and biological rhythms began in Earth's ancient seas, where tidal forces created regular patterns of exposure and submersion that shaped the earliest life forms. Over millions of generations, organisms developed internal clocks synchronized to lunar phases, creating chronobiological systems that persist in modern species, even when they no longer live in tidal environments. These lunar rhythms operate alongside circadian clocks, creating complex biological timing systems that coordinate reproduction, feeding, and migration with cosmic precision. Many marine species rely on moonlight for fundamental navigation, with sea turtle hatchlings providing one of the most dramatic examples of lunar dependence. Newly hatched sea turtles use the moon's reflection on ocean waves to find the water after emerging from beach nests, a behavior that has evolved over millions of years to ensure successful ocean entry. During blood moon events, this crucial navigation system fails as the familiar bright reflection disappears, leaving hatchlings disoriented and vulnerable to predation or exhaustion as they search for the sea. Nocturnal predators throughout the animal kingdom have evolved hunting strategies precisely timed to lunar phases, taking advantage of varying light levels to optimize their success rates. Lions in Africa increase their hunting activity during dark moon periods, when prey animals cannot detect their approach as easily, while many owl species adjust their foraging patterns to coincide with optimal lunar illumination that helps them spot small mammals. During blood moon events, these predator-prey relationships experience temporary disruption as established light-dependent behaviors encounter unexpected conditions. Coral reefs demonstrate perhaps the most spectacular example of lunar biological synchronization through mass spawning events that occur on specific nights following full moons. These extraordinary reproductive gatherings involve multiple coral species, simultaneously releasing billions of eggs and sperm into the water column, creating underwater snowstorms of genetic material that ensure cross-fertilization and species survival. The precise timing depends on lunar phase, water temperature, and tidal cycles, with many species spawning only during the days immediately following full moon when tidal currents provide optimal conditions for gamete dispersal. During blood moon events, coral spawning behavior shows measurable disruption as the changed light conditions interfere with the environmental cues that trigger reproductive timing. Some coral species may delay spawning until the next lunar cycle, while others may proceed with reduced coordination among colony members, potentially affecting reproductive success across entire reef systems. Marine plankton undertake one of Earth's largest daily migrations, moving vertically through ocean water columns in response to changing light levels throughout day and night cycles. This DL vertical migration involves trillions of microscopic organisms that rise toward the surface during darkness to feed on phytoplankton, then descend to deeper waters during daylight to avoid visual predators. Moonlight intensity affects these migration patterns, with brighter full moons causing plankton to remain deeper in the water column throughout the night. Blood moon events create confusion in these massive plankton migrations, as the sudden change in lunar illumination disrupts the light cues that govern vertical movement patterns. The altered migration behavior cascades through marine food webs, affecting fish feeding patterns, whale distribution, and ocean productivity in ways that demonstrate how cosmic events influence entire ecosystem dynamics. Scientific studies conducted during lunar eclipses have documented remarkable changes in animal behavior across diverse species and environments. Birds often fall silent during blood moon totality, with nocturnal species that normally remain active showing signs of confusion or returning to roost as if dawn were approaching. Domestic animals frequently display unusual behaviors during eclipses, including increased barking or meowing, restlessness, and apparent anxiety that suggests they perceive the cosmic event as a potential threat. Wild mammals show varied responses to blood moon conditions, with some species becoming more active as they interpret the dim red light as favorable for foraging, while others retreat to protective cover as if responding to predator presence. These behavioral changes reveal how deeply lunar rhythms are embedded in animal psychology and survival strategies. Insects demonstrate some of the most dramatic responses to lunar eclipse conditions, with many nocturnal species altering their flight patterns, mating behaviors, and feeding activities. Moths that normally navigate using moonlight for orientation become disoriented during blood moon events, while fireflies may change their flashing patterns in response to the altered light environment. These insect behavioral changes can affect pollination patterns and predator-prey relationships throughout terrestrial ecosystems. Recent research in chronobiology has revealed that lunar biological rhythms may persist even in humans, despite our largely artificial light environments. Some studies suggest that human sleep patterns, hormone production, and mood variations may still show subtle correlations with lunar phases, indicating that blood moon events might trigger measurable physiological responses in people sensitive to cosmic rhythms. The biological responses to blood moons may represent evolutionary vestiges of ancient survival mechanisms that helped ancestral organisms cope with unpredictable environmental changes. Sudden darkening of the night sky could have signaled volcanic eruptions, massive fires, or other catastrophic events that required immediate behavioral adaptation. The genetic memory of these responses may persist in modern species as innate reactions to cosmic disruption. Modern conservation biology increasingly recognizes the importance of lunar cycles in wildlife management and protection strategies. Sea turtle conservation programs must account for lunar timing in beach protection efforts, while marine protected areas consider lunar spawning cycles when establishing fishing restrictions. Blood moon events require special consideration in these conservation efforts, as they represent periods when normal behavioral patterns may be disrupted. Urban lighting pollution has already disrupted many lunar biological rhythms by masking natural moonlight cycles, creating ecological light pollution that affects everything from insect behavior to bird migration patterns. Blood moon events provide rare opportunities to study how wildlife behaves under more natural lighting conditions, even in urban environments where artificial illumination normally overwhelms cosmic light sources. Perhaps most remarkably, the biological responses to blood moons demonstrate that life on Earth remains intimately connected to cosmic phenomena, despite billions of years of evolution and the development of complex ecosystems that might seem independent of astronomical events. These connections reveal that Earth's biosphere continues to dance to cosmic rhythms, where even familiar celestial events like lunar eclipses can trigger biological responses that echo through evolutionary time and remind us of our planet's place within the larger cosmic environment. The study of biological responses to blood moons thus provides insights not only into animal behavior and ecology, but into the fundamental ways that life on Earth remains synchronized with cosmic cycles that have governed biological timing since the earliest emergence of complex organisms in ancient seas. Space missions have revolutionized our understanding of blood moons by providing observations impossible from Earth's surface, transforming these celestial events from two-dimensional sky phenomena into fully comprehensible three-dimensional cosmic choreography that reveals the true scale and complexity of planetary shadows cast across the void. These space-age perspectives have literally elevated human consciousness above the atmospheric veil that has limited terrestrial observers for millennia, offering viewpoints that our ancestors could only imagine in their most ambitious dreams of cosmic flight. Astronauts aboard the International Space Station have become the first humans to witness blood moons from above Earth's atmosphere, experiencing these events as participants in cosmic mechanics, rather than distant observers watching celestial projections. From their orbital perspective, 400 kilometers above Earth's surface, crew members see how our planet's shadow creates a vast cone of darkness extending over 1 million kilometers into space, with the moon appearing as a small disk passing through this three-dimensional shadow structure. These orbital observations reveal details completely invisible from Earth's surface, including the thin ring of red and orange light that surrounds our planet's edge during eclipse events. This atmospheric ring, created by sunlight refracted through Earth's gaseous envelope, appears from space as a brilliant corona of warm colors that transforms our blue marble into a cosmic lighthouse, broadcasting red illumination across interplanetary distances. Astronauts describe this phenomenon as one of the most beautiful sights visible from orbit, where Earth's atmosphere becomes a visible light source painting the cosmos in sunset hues. The International Space Station's unique orbital position allows real-time documentation of eclipse progression from multiple perspectives as the station orbits Earth every 90 minutes. Crew members can observe the advancing shadow edge from space while simultaneously witnessing the blood moon effect as seen from Earth's night side, providing comprehensive views of the entire eclipse system operating across multiple scales of space and time. Lunar orbiters have provided even more dramatic perspectives by photographing Earth during blood moon events from the moon's vicinity, showing how our planet appears from 250,000 miles away during these cosmic alignments. The Lunar Reconnaissance Orbiter and other spacecraft have captured images showing Earth as a brilliant blue disk surrounded by the thin ring of atmospheric light that creates the blood moon illumination, demonstrating how eclipse events look from the moon's perspective. These lunar distance photographs reveal Earth's shadow as it actually exists in space, not as the simple circular projection we observe from our planet's surface, but as a complex three-dimensional structure with clearly defined umbral and penumbral regions. The shadow appears as a dark cone extending behind Earth, with the lunar spacecraft occasionally capturing dramatic images of Earth partially eclipsing the Sun as seen from lunar orbital distances. Space-based thermal imaging systems have revolutionized our understanding of how the lunar surface responds to eclipse conditions, measuring temperature changes across the moon with precision impossible from Earth-based telescopes. These orbital instruments reveal that different lunar materials cool at dramatically different rates during eclipse, creating detailed temperature maps that provide insights into surface composition, density, and thermal conductivity properties. The thermal observations show that lunar rocks and boulders retain heat much longer than the fine regolith dust that covers most of the surface, creating temperature contrast maps that reveal buried geological structures and impact crater details invisible to optical imaging. Some regions show temperature variations that persist for hours after eclipse totality, indicating subsurface rock formations or unusual mineral compositions that affect heat retention properties. Advanced spacecraft have captured the dynamic nature of eclipse progression with time-lapse imaging that shows Earth's shadow racing across the lunar surface at speeds of approximately 1,700 kilometers per hour. The Lunar Reconnaissance Orbiter has documented this shadow movement with such high resolution that individual crater walls and mountain peaks can be seen entering and leaving the shadow zone, transforming the blood moon from a gradual celestial transformation into a dramatically dynamic event. These high-speed shadow observations reveal the true nature of eclipse mechanics, where the apparent slow progression visible from Earth actually represents rapid motion of a shadow boundary traveling at speeds that would circumnavigate our planet in less than 24 hours. The spacecraft imaging shows how this shadow edge creates sharp transitions between illuminated and eclipsed lunar terrain, with some geological features experiencing eclipse onset within minutes. Robotic spacecraft, positioned at gravitationally stable Lagrange points, have provided unique perspectives on eclipse events by observing both Earth and Moon simultaneously during blood moon occurrences. These distant vantage points show the entire Earth-Moon system as it appears from space, with Earth's shadow cone visible as it extends toward and engulfs the Moon during eclipse progression. The European Space Agency's Gaia Observatory, positioned at the L2 Lagrange point 1, 5 million kilometers from Earth, has captured images showing the eclipse system from outside the Earth-Moon gravitational sphere of influence. These observations provide the most comprehensive views possible of eclipse mechanics, showing how planetary shadows extend across interplanetary distances and interact with other celestial bodies. Modern spacecraft carry sophisticated spectrometers that analyze the light reflected from the Moon during eclipse events, providing detailed information about how Earth's atmosphere affects sunlight transmission during blood moon conditions. These space-based spectroscopic measurements reveal atmospheric composition, aerosol concentrations, and trace gas distributions with precision impossible from ground-based observations, turning each blood moon into a comprehensive atmospheric science experiment. The spectrometric data collected during eclipse events has contributed to climate science by providing independent measurements of atmospheric transparency and composition that complement ground-based monitoring systems. Space-based eclipse observations have detected the effects of volcanic eruptions, wildfire events, and atmospheric pollution on eclipse brightness and color, demonstrating how human activities affect even cosmic phenomena through their impact on atmospheric clarity. Perhaps most remarkably, spacecraft observations during blood moons have revealed previously unknown aspects of space-environment interactions, including how Earth's magnetic field affects charged particles in the space around the Moon during eclipse events. Plasma instruments on lunar orbiters have detected changes in the space environment as the Moon passes through different regions of Earth's magnetosphere, providing insights into the complex electromagnetic relationships between Earth and its satellite. Future space missions will continue expanding our eclipse observation capabilities through advanced instruments and more distant observation points. Proposed telescopes positioned throughout the solar system could provide unprecedented views of eclipse events from multiple perspectives simultaneously, creating comprehensive three-dimensional maps of how planetary shadows propagate through space and interact with other celestial bodies. The spacecraft perspective has thus transformed blood moons from mysterious celestial omens into precisely understood examples of cosmic mechanics, operating according to physical laws that govern planetary motion throughout the universe. These space-age observations have elevated human understanding from ground-based wonder to orbital comprehension, demonstrating how technological advancement continuously expands our ability to understand cosmic phenomena from perspectives that transcend the limitations of terrestrial observation and reveal the true three-dimensional nature of astronomical events. At the quantum level, the blood moon represents a massive information transfer event of staggering complexity, where countless billions of photons carry encoded messages about Earth's atmospheric conditions across nearly 400,000 kilometers of vacuum to the lunar surface, creating what may be the largest natural quantum communication system observable in our cosmic neighborhood. This quantum perspective transforms the familiar blood moon from a simple optical phenomenon into a demonstration of how information, energy, and consciousness intersect at the most fundamental levels of physical reality. Each individual red photon reaching the Moon during eclipse totality has survived an extraordinary quantum mechanical journey through Earth's atmosphere, encountering and interacting with molecules, particles, and electromagnetic fields that collectively encode information about our planet's gaseous envelope. These photons carry quantum signatures, subtle alterations in their energy states, polarization properties, and wave function characteristics that preserve detailed records of every atmospheric encounter during their passage from the edge of space to the lunar surface. The quantum information encoded in eclipse light operates through principles that challenge classical understanding of how information travels through space. Unlike classical communication systems that transmit discrete bits of data, quantum information exists in superposition states where multiple pieces of information coexist simultaneously until observation collapses the wave function into specific measured values. The photons illuminating the blood moon carry quantum superpositions of all possible atmospheric interactions, creating information density that exceeds anything achievable through classical communication methods. Quantum physicists study how Earth's magnetic field affects the polarization states of eclipse light, using the blood moon as a natural laboratory for investigating quantum field interactions on astronomical scales. The planet's magnetosphere creates subtle alterations in photon polarization that reveal information about magnetic field strength, configuration, and temporal variations during eclipse events. These quantum polarization measurements provide insights into magnetospheric physics that complement traditional space-based magnetic field monitoring systems. The atmospheric layers that create blood moon illumination through refraction also affect the quantum coherence properties of light in measurable ways. Quantum coherence, the degree to which photons maintain their wave-like properties during propagation, becomes degraded through interactions with atmospheric molecules, creating decoherence patterns that reveal information about atmospheric density, composition, and turbulence. Advanced quantum optical instruments can measure these decoherence effects to study atmospheric physics with unprecedented sensitivity. The process of atmospheric refraction that bends sunlight around Earth's edge during eclipse involves quantum mechanical interactions between individual photons and atmospheric molecules that operate according to the fundamental principles of quantum electrodynamics. Each scattering event represents a quantum measurement that collapses photon wave functions while transferring information about molecular properties to the light field, demonstrating how quantum mechanics operates on scales from individual particles to planetary atmospheres. Theoretical physicists have proposed using the precise timing and geometry of lunar eclipses for quantum communication experiments that could test the limits of quantum information transmission across astronomical distances. The moon could serve as a massive quantum reflector for experiments involving quantum key distribution, where encrypted information encoded in photon quantum states travels from Earth to lunar retroreflectors and back, creating secure communication channels protected by the fundamental laws of quantum mechanics. These proposed lunar quantum communication systems would utilize the quantum no-cloning theorem, which prevents perfect copying of unknown quantum states to create unbreakable encryption protocols. Any attempt to intercept quantum encrypted messages traveling the Earth-Moon distance would necessarily disturb the photon quantum states, making eavesdropping detectable through measurements of quantum state fidelity after the round-trip journey. The blood moon environment provides unique opportunities to study how quantum entanglement, Einstein's spooky action at a distance, might be affected by gravitational fields and cosmic scale phenomena operating across interplanetary distances. Quantum entanglement experiments conducted during eclipse conditions could test whether entangled photon pairs maintain their correlations when one photon travels through Earth's gravitational field while its entangled partner remains in free space. These gravitational quantum experiments could reveal whether general relativistic effects influence quantum mechanical correlations in ways that current theory doesn't predict. Some speculative models suggest that gravitational fields might affect quantum entanglement through mechanisms involving the coupling between gravity and quantum field fluctuations, potentially leading to new physics at the intersection of quantum mechanics and general relativity. Advanced quantum optical experiments during blood moon events study how atmospheric turbulence affects quantum state preservation in light-traveling astronomical distances. The atmospheric layers that create eclipse illumination also introduce random phase shifts and amplitude variations that can destroy quantum coherence, providing natural laboratories for studying quantum decoherence in complex, time-varying media that cannot be replicated in terrestrial laboratories. The quantum vacuum fluctuations underlying empty space itself may contribute to subtle effects in blood moon illumination through processes involving virtual photon interactions and zero-point energy variations. Some theoretical models predict that astronomical-scale quantum phenomena might become detectable in precision measurements of eclipse-like properties, potentially revealing new aspects of quantum field theory operating on cosmic scales. Recent developments in quantum sensing technology have enabled detection of quantum effects in astronomical observations that were previously impossible to measure. Quantum-enhanced interferometry and photon correlation measurements during eclipse events can detect quantum signatures in blood-moon illumination with sensitivity approaching fundamental quantum limits, opening new windows for studying quantum phenomena in astronomical environments. The emergence of quantum biology as a scientific discipline adds another layer to quantum interpretations of blood-moon phenomena, suggesting that some biological systems might be sensitive to quantum properties of light in ways that could make eclipse events detectable at the molecular level. Quantum effects in photosynthesis, avian navigation, and other biological processes might create pathways for life forms to respond to quantum changes in eclipse illumination. Perhaps most profoundly, the quantum perspective on blood moons reveals how consciousness itself might connect to cosmic phenomena through quantum mechanical processes. Some interpretations of quantum mechanics suggest that conscious observation plays a fundamental role in collapsing quantum wave functions, implying that human consciousness might participate in determining which quantum possibilities become actualized during eclipse events. These quantum connections transform blood moons from classical astronomical events into windows for exploring the deepest mysteries of physics and consciousness, where the familiar red glow carries encoded information about quantum reality operating across scales from subatomic particles to planetary systems. The quantum nature of eclipse illumination demonstrates how even apparently simple cosmic phenomena involve fundamental quantum processes that connect local atmospheric conditions to universal principles governing information, energy, and the nature of reality itself. The study of quantum aspects of blood-moon phenomena thus represents a convergence of astronomy, quantum physics, and consciousness studies that may ultimately reveal new understanding about how quantum mechanics operates in cosmic environments, and how conscious observation might influence astronomical phenomena through quantum mechanical pathways that bridge the gap between mind and cosmos. Blood moons serve as natural archives of Earth's climate history, preserving information about atmospheric conditions in the detailed observations recorded by countless generations of skywatchers, who transformed their awe and fear into written records that now provide climate scientists with invaluable data spanning over a millennium of atmospheric change. These celestial chroniclers, writing by candlelight in monastery scriptoriums or recording observations in royal courts, unknowingly created one of the longest continuous climate datasets available to modern researchers. Medieval chroniclers across Europe, Asia, and the Islamic world meticulously documented lunar eclipses with descriptions that reveal far more than their authors intended about past atmospheric conditions. Monks recording dark eclipses where the moon disappeared entirely, or blood moons that glowed like embers, were actually documenting atmospheric transparency levels that correlate directly with global climate patterns, volcanic activity, and air quality conditions that existed centuries before instrumental measurements began. These historical descriptions follow remarkably consistent patterns that allow climate scientists to extract quantitative information from qualitative observations. Chronicles describing eclipses as bright as burnished copper indicate clear atmospheric conditions with minimal dust or aerosols, while accounts of dark eclipses barely visible to the eye reveal atmospheric loading from volcanic eruptions, massive fires, or unusual dust storm activity. The consistency of these descriptions across different cultures and geographic regions validates their scientific utility as climate proxy data. The color and brightness variations documented in historical eclipse records correlate directly with global temperature patterns, atmospheric circulation changes, and air quality conditions that affect how sunlight scatters through Earth's gaseous envelope. During the medieval warm period, roughly 900 to 1300 CE, eclipse descriptions generally emphasize bright, vivid red coloration suggesting clear atmospheric conditions. Conversely, eclipse accounts from the Little Ice Age period, approximately 1300 to 1850 CE, frequently mention darker, more somber appearances that may reflect increased volcanic activity or changes in atmospheric circulation patterns. The most dramatic correlations appear in eclipse records following major volcanic eruptions, where historical accounts describe eclipses becoming virtually invisible or appearing deep brown rather than red. The 1815 eruption of Mount Tambora in Indonesia, which caused global climate disruption and crop failures worldwide, coincided with eclipse descriptions from Europe and Asia, mentioning unusually dark lunar eclipses that persisted for over 2 years following the eruption. Modern ice core analysis from Greenland and Antarctic drilling projects has provided independent verification of these historical eclipse records by revealing elevated sulfur dioxide levels that correspond precisely to periods when chronicles describe particularly dark lunar eclipses. These ice core sulfur spikes indicate volcanic activity that injected massive quantities of aerosols into the stratosphere, creating the atmospheric conditions that darkened eclipse illumination and preserved evidence of these events in both geological and written records. The correlation between ice core chemistry and eclipse brightness descriptions demonstrates the remarkable accuracy of historical observations and validates the use of eclipse records as quantitative climate data. Volcanic eruptions that left no other historical traces have been identified through eclipse darkness descriptions that correlate with sulfur spikes in ice cores, revealing previously unknown climate-forcing events that affected global atmospheric conditions. Climate modeling groups now routinely incorporate historical eclipse observations into their reconstructions of past atmospheric states, using eclipse brightness and color descriptions to test whether computer simulations accurately reproduce the atmospheric conditions that would create observed eclipse characteristics. These models must account for volcanic aerosol distributions, atmospheric circulation patterns, and seasonal variations in dust loading to match historical eclipse descriptions with calculated atmospheric transparency values. The validation process involves running climate models for specific eclipse dates and comparing simulated atmospheric conditions with observed eclipse properties described in historical records. Successful matches between modeled and observed eclipse characteristics provide confidence in climate model accuracy, while discrepancies reveal areas where models may not adequately represent past atmospheric processes or volcanic impact patterns. The study of blood moon climate archives has revealed several previously unknown volcanic eruptions and atmospheric disturbances that significantly affected global climate, but left no other reliable historical traces. Eclipse darkness descriptions from the 6th century CE, combined with ice core evidence, have identified a massive volcanic event around 536 CE that caused global cooling and crop failures across multiple continents, leading to famine and social disruption that may have contributed to the fall of various civilizations. These cryptic volcanic events, detected only through eclipse records and ice core chemistry, demonstrate how astronomical observations can reveal climate history that would otherwise remain hidden. The global visibility of lunar eclipses creates worldwide documentation of atmospheric conditions that no other natural phenomenon can provide, with comparable temporal precision and geographic coverage. Modern eclipse observations serve as crucial baseline data for understanding how human activities might be changing atmospheric light, scattering properties through industrial pollution, urban aerosols, and greenhouse gas emissions. Contemporary eclipse brightness measurements provide reference standards for evaluating whether anthropogenic atmospheric changes are affecting eclipse appearance in detectable ways. Systematic eclipse monitoring programs now coordinate observations from multiple geographic locations to study regional variations in atmospheric transparency and aerosol loading. These modern observations reveal how industrial pollution, wildfire smoke, and dust storms create measurable variations in eclipse brightness across different regions, demonstrating the connection between local air quality and global atmospheric optical properties. Satellite-based atmospheric monitoring systems complement ground-based eclipse observations by providing real-time data about aerosol concentrations, atmospheric circulation patterns, and trace gas distributions during eclipse events. This combination of traditional eclipse observation and modern space-based measurement creates comprehensive data sets that advance understanding of atmospheric optics and climate processes. Climate scientists use eclipse observations to study how rapidly atmospheric conditions can change. Following major perturbations such as volcanic eruptions or massive wildfire events, the recovery time for eclipse brightness to return to normal levels following atmospheric disturbances provides insights into atmospheric residence times for various aerosol types and the efficiency of atmospheric cleansing mechanisms. Perhaps most importantly, the Blood Moon Climate Archive demonstrates the value of citizen science and historical observation in understanding long-term climate variability. The dedicated observations of medieval chroniclers, amateur astronomers, and modern eclipse enthusiasts have created an irreplaceable scientific resource that spans nearly 1,000 years of atmospheric monitoring, providing context for understanding current climate change within the framework of natural atmospheric variability. The continuing growth of this climate archive through modern eclipse observations ensures that future climate scientists will have access to even longer data sets for studying atmospheric change and evaluating the accuracy of climate models. Each blood moon adds another data point to this remarkable archive, connecting contemporary atmospheric science to the patient observations of countless generations who looked up at the darkened moon and carefully recorded what they saw, unknowingly contributing to humanity's understanding of Earth's changing climate across centuries of atmospheric evolution. Einstein's theory of relativity adds subtle but measurable effects to blood moon observations, transforming these familiar celestial events into precision laboratories for testing the fundamental nature of space and time across cosmic distances, where the curved geometry of space-time and the relative motion of massive bodies create effects that challenge our intuitive understanding of reality. These relativistic influences operate at levels so minute they remained undetectable until humanity developed instruments capable of measuring time to billionths of a second and frequencies to parts per trillion. The moon's position deep within Earth's gravitational field creates measurable gravitational redshift effects that alter the wavelength of eclipse light